Hi, everybody. This is Dr. Nigro with a chem calculation screencast. This screencast is going to focus on integrated rate laws, in particular for zero, first, and second order reactions. If you have questions about relative rates or differential rate laws, please make sure you refer to those specific screencasts. All right, so what is an integrated rate law? All right, similar to differential rate laws, it's reactant focused and it is basically the mathematical integration of the differential rate law. All right. There are many things that you can use these rate laws to do. All right. All right. So we can use to first, all right, you can calculate oops, the concentration of reactant at any time during the reaction. All right. You can also estimate time needed to reach a certain concentration of a reactant. All right, so that is new. Our rate laws for our differential rate laws, time wasn't in there anywhere. Time is going to be back as a variable in these integrated rate laws. All right. Three, depending on what I know, I can calculate the initial concentration of the reactants. All right, present at the beginning of that reaction. All right, I can also calculate my rate constant K. And finally, I can calculate the half-life of my reactant, which is called T1/2. All right, so all of those can be done with these integrated rate laws, which is very different than what you can do with the differential rate laws. So it's a very useful way to look at chemical kinetics. All right, now I've got this table here. This table is super handy. I put it on here rather than try to write it all out, just so we can see what's going on. All right, so the first thing you can see, I've got a column here for zero, first, and second order reactions. And then I've got the differential rate laws here. So for zero order, rate is equal to K. For first order, rate is equal to K times the concentration of A. And then for second order, rate is equal to K times the concentration of A squared. All right, so those are our differential rate laws. And as you can see, if I plot the change in concentration versus time, all right, for our zero order, we get this linear spot until we run out of reactant because this depends only on K, which is a constant. All right, now you can see that as we move to first and second order, we start to have curves present instead of linear graphs. And so that first tells us that we have something besides a zero order. The steeper it is, the more likely it is to be a higher order, but it's a little tough to tell from these concentration versus time plots. So you're better off using what I call the straight line plot to determine what your order is. All right. If you plot concentration versus time and get a straight line, that's going to be a zero order. All right. If you plot concentrations versus time and get a curve, then it's not zero order. If you plot the natural log of your concentration versus time and get a straight line, all right, then that tells you you are first order. All right. And if you plot 1 over the concentration versus time and get a straight line, then you know you are second order. All right, so recognizing which of these three plots gives you a straight line and then tells you the order is very, very handy because if you're given a plot, you can immediately look at it and decide what order it is. All right. The other thing to keep in mind is what this, sorry, is what these straight lines mean. All right, remember, straight lines, linear plots, are equal to y equals m times x plus b. All right, so if we look at our zero order, right, so y is concentration. All right, the slope here is going to be equal to k. All right, and then x is going to be time. So when we rewrite it, we end up with this integrated rate law, all right, where the concentration of A is equal to the initial concentration minus K times T. All right, now we know the negative sign should be there because the slope is high to low, so it's a negative slope. All right, if we move over to our first order plot, it's going to be the natural log versus time. All right, so we write the formula for that line and we get the natural log of A is equal to the natural log of the initial amount minus K times T. All right, so again, negative for our slope because we have moving from high to low in terms of our plot. All right, and then finally for our second order, our integrated rate law, hold on, let me box that in, is 1 over the concentration equals 1 over the initial concentration plus K times T. And this time we know the slope is positive because it's going from low to high. So it gives us this integrated rate law. All right. So if you are given data and asked to determine the order of the reaction, you need to decide which of these three is going to give you a straight line. All right. So if we think about it, here is some data. All right. If we increase the concentration of M, there is no increase in the rate. So this has to be zero order. All right. If we move from here to here and we see an increase of 2 in our concentration, and we look from here to here and we see an increase of 2, all right, that tells us this is first order. All right. Over here, if we increase the concentration by a factor of 2, but we see an increase by a factor of 4, then we know that is second order. So that's another way to determine the order. All right. Now, half-life is something we haven't talked about all that much. All right. It's represented by T with a subscript 1/2. All right. This is the time needed for the concentration of your reactant to decrease to half the original amount. All right, now that halving happens in succession. So you have your first half-life, so then you have half, and then if that goes down by half, that's the second half-life. If that goes down by half, that's the third and the fourth and the fifth. All right, so you can calculate it over and over and over just by using a new initial concentration. All right, for a zero order reaction, the T1/2 will decrease for each half. I'm going to call it halvings. All right, so in other words, the time it takes to go from half to the next half is going to be less than the time it took to go from the initial to the first half. All right. For a first order, the half life is constant. All right, so it doesn't matter which half-life you're talking about, the time it takes to get to the next one is the same. All right, and then finally, second order, all right, your T1/2 will increase with each halving. All right, now this is all right there in the formulas. All right, you can see right here is the half-life formula for a zero order reaction. All right, as this number gets smaller, then this number is going to get smaller. So each initial amount for your halves is going to lead to a decrease in that time. All right, for first order, you can see the only variable in this equation is K, which is a constant. All right, so that means it doesn't matter which halving you're talking about, the half-life will be the same. And then finally, for second order, you can see the concentration of your initial concentration is now in the denominator. So if that number gets smaller, then your half-life will get larger. Okay. And then finally, we've got the units for K. We've talked about that already in terms of our differential rate laws. It's the same thing here. As you go up in order, the molar is going to increase in that denominator. So 0 order, it's up top. First order, there isn't one. Second order, there's one in the bottom. All right, so what can we do with this information? Well, we can solve a lot of mathematical problems. All right, so we're going to go through a couple different ones. A couple things to keep in mind. These are formula-driven problems for the most part, so you need to list out your variables and make sure you're paying attention to which order the reaction is, because that's going to determine what formulas you can use. All right, so here a reaction is first order in A, takes 6.35 seconds for the concentration of A to change from 1.55 molar to 0.0855 molar. What is the half-life? All right, so I always like to start out by listing out what I've been given. So my initial amount of A is 1.55 molar. My final amount of A for this problem is 0.80855 molar, and I've got a time here of 6.35 seconds. And it wants to know, well, what is the half-life? And it's first order. All right, so if I look back up at my table, the half-life for a first order reaction depends on K, which I don't have. So the first thing I'm going to have to do here is calculate K. So I know that the natural log of A equals the natural log of A naught minus K times T. All right, so what that gives me is the natural log of 0.0855 divided by 1.55 minus, oops, equals, sorry, messed that up, negative K times 6.35 seconds. All right. Make sure you know where the natural log button is on your calculator. It's going to be important for this part of the unit. All right. So once I work this out, I find that K is equal to 0.0937. This is first order, so that's per second. All right. That's not going to be quite as obvious as it is with our other ones. So make sure you remember what that unit should be. All right, now with that, I can go to my T1/2 calculation. So that's 0.693 divided by K. So 0.693 divided by 0.0937 per second. That's going to flip up. So the second is in the denominator of the denominator. It's become a numerator, which is great because that means I have a time unit here. And I get 7.40 seconds. So it's going to take 7.40 seconds for this sample to go from its initial amount to half. Okay. Next, we have a first order reaction. We have a K value of 5.67 per second and an initial amount of A of 0.650. How long will it take to reach 0.035? All right, so again, I have an initial amount of 0.650 molar. I have a final amount of 0.0350 molar. I have a K value of 5.67 per second, and I'm asked to find the time it's going to take with a first order reaction. All right, so again, I'll use my natural log formula. Now, you may be saying to yourself, well, do I need to memorize these formulas? And the answer is no. They will be on your reference sheet. However, you do have to remember which one is 0, first, and second. That is not listed on there. All right. All right. So that means the natural log of A divided by A naught. So 0.035 molar divided by 0.65 molar equals negative 5.67 per second times time. All right. So I'll take the natural log of that division, then I'm going to divide that by negative 5.67, and I find that to move from this amount to 0.035 molar is going to take 0.515 seconds. All right, now you might say, well, that's really fast, and it is, but your proportionality constant is not small, which means the reaction is probably running pretty quickly. All right, so that's a reasonable answer. Okay, here we have a second order reaction with a K value of 2.46 per molar per second. We have an initial amount of A at 0.67 molar, and we're asked what is the concentration of A after 2.10 seconds. All right, so again, second order this time. Initial amount of A, 0.670 molar. Final amount is our unknown. All right, we're also given K, 2.46 per molar second, and we have a time of 2.10 seconds. All right, so again, formula driven, but choose the right formula. All right, so in this case, because it's second order, it's 1 over A equals 1 over A naught plus K times T. All right, so 1 over A is going to be equal to 1 over 0.670 molar time, whoops, not times, plus 2.46 per molar second times 2.10 seconds. All right, so the seconds are going to cancel, and both of the what remains will be per molar. All right, now here's where you have to be careful. When I do all of the math over here, I get 6.66 per molar, and it is very tempting to stop because you're like, oh, I'm done, I got a number. But you have to remember that's equal to 1 over A. All right, so you need to invert both of those. So in other words, A is going to be equal to 1 over 6.66 per molar, all right, which is equal to 0.150 molar. Now, how do you make sure that you do that? Well, first of all, look at the unit. You cannot have a concentration in per molar. That is not a concentration unit. Concentration unit is molar. Second, we have a reactant and we are using it up. So it makes no sense for us to start with 0.670 molar and end up with 6.66 molar. All right, that shows an increase in the amount, and that cannot be correct for our reactant. 0.150 molar, however, is less than our initial amount, which is reasonable. All right, next. The half-life of a second order reaction is 0.0550 seconds. If the initial concentration of A is 0.15 molar, what is the rate constant? Oh, there's a lot going on here. All right, so T1 half, second order, 0.0550 seconds. All right, the initial concentration is 0.150 molar, and we are asked to find the rate constant. All right, so we got to think about what we need to do here. All right, personally, I would use my half-life formula for this second order reaction. All right, so if we look, P1 half or second order reaction is equal to 1 over K times that concentration initially. All right, so everything we need is in here. I might do a little rearranging. So I might say that K is equal to 1 over T1 half times that initial concentration, just to make the math easier. All right, so I end up with 1 over 0.0550 seconds times 0.115 molar, and I end up with 121, and the unit here would be molars times seconds, which is second order, so that is a reasonable unit. All right. Now, what if you don't remember that formula? What are you going to do? All right. Well, the easiest thing to do is to remember that that half-life is the time it takes to go from the initial amount to half. All right. So I could use my 1 over A equals 1 over initial A plus K times T to find that K value. If I take half of that initial amount, which is 0.075 molar, equal to 1 over 0.15 molar plus K times the 0.0550 seconds, because that is the time it needs to go from 0.15 to 0.075 in terms of concentration. All right. If we do that and do our math correctly, we should end up with a K value here of 121 per molar second. So you can see either way is going to work. This half-life formula is not on the reference sheet. So knowing how to do it this way is not a bad idea. All right, then finally, 1-0 order. So reaction is 0th order in A if the concentration of A is 0.156 molar after 1.25 seconds. What was the initial concentration of A? The rate constant is 1.75 molar per second. All right, so what do we have? We have a zero order reaction. We have an amount of A that's 0.156 molar, and we're asked to find that initial amount after 1.25 seconds have elapsed and our rate constant is 1.75 molar seconds. All right, so this is zero order. So we need to use our zero order formula, which is A is equal to A naught minus K times T. All right, so 0.156 molar is equal to our unknown minus 1.75 molar per second times 1.25 seconds. That's going to cancel our seconds for us, leaving us with molar, which is what we need for that A naught. All right, plug and chug, and we end up with 2.34 molar as the initial concentration of our reactant. Now that is reasonable. The reaction has been running, so that initial amount should be higher than what we have after 1.25 seconds. Okay, I strongly suggest that you focus on these straight line plots as a way to determine which order your reaction is. These formulas should be on the reference sheet, so you don't need to memorize them, but you do need to know which goes with which. And then at the very least, this half-life formula is on the reference sheet, but the other two, you may have to use mathematics to figure out what those half-lives are. And then finally, those units of K, which we talked about with their differential rate laws, still hold here for the integrated rate laws. Okay. Let me know if you have any questions.